Hello and welcome to a new lecture on artificial intelligence. Today we're going to study constraint satisfaction problems. In the previous lecture and also this lecture, we are trying to solve problems using search algorithms. First, let's find out what type of problem are we going to target. Some problems are standard search problems that can be solved using the previous discussed algorithms like local search or adversarial search. In these algorithms, we need to specify the states and actions. And also, we need to define the state space graph. Then the algorithm traverses the graph and tries to find out a path from the initial state to the goal state. Sometimes we need to find the shortest path, but sometimes just we need to reach the goal in any price. And also we have seen that there are some cases where there are some enemies or opponents as well. But a special subset of search problems are constraint satisfaction problems, or CSPs in short. In CSPs, state is some variable that can get value from a specific domain. It means they cannot have any value. And here, the goal is satisfying a set of constraints that specifies a set of allowed values for the variables. CSP allows useful general-purpose algorithms with more power than standard search algorithms. Here is an example. In this example, we want to color Australian map in such a way that there is no two adjacent cells with the same color. So you can see here we have some variables, and the variables are provinces, like for example, Western Australia, North Territory, Queensland, South Australia, New South Wales, Victoria, and Tasmania. We define our variables as the abbreviation for each one, like WA, NTQ, NSW, SA, and T for each province. Then we have domain. Domain is the set of available values for each variable. It can get red color, green color, or blue color. So here we have a constraint, and the constraint says two provinces must not have the same color. It means two provinces should have different color. If this is red, this cannot be red, and this cannot be red. So red, green, blue is okay. And the same that you can see here. We can define the constraint implicitly. It means WA cannot be equal to NT. It means they cannot have the same color. Or we can go for explicit way. For example, we can say WA NT. It can be red, green, red, blue, and etc. And we want to have a solution that is complete and also consistent in terms of assignment. What it means? Complete, it means all the variables must have a value, and there is no variable left behind without a value. And it must be consistent. It means each variable can get a value from its own domain and no constraint is violated. So for example here, WA can get red, NT can get green, then Queensland can get red, right? Because it's not neighbor of WA. Then NSW can get green, V can get red, SA can get blue, and Tasmania can get any color because it's not neighbor, right? It's an island. We also can consider the n-queens problem as a CSP. If we increase the number of queens, then it's not easy to solve the problem using the previous algorithms. If we have, for example, 1,000 queens and the board is 1,000 by 1,000, then CSP can work better. We can formulate in different ways. For example, in formulation number 1, we have an objective. The objective is to assign each queen to one cell in such a way that no queen can kill each other, right? So for example, this queen can be here because there's no queen here, no queen here, no queen here, and no queen here. Here we have some variables. We assign one variable to each queen. For example, X, I, and J. It means that in cell I and J, there is a queen. The domain for each variable is 0 or 1. 0, it means there is no queen in this cell, and 1 is there is a queen in this cell. Then we define our constraints. We need to define constraints because we want to take care of them to not be violated. We try to do it in an implicit way. So here you can see sum of all X, I, and J should be equal to N. It means a queen is in the row I and J, and sum of them should be equal to the number of queens that we have. So sum of the cells that has a queen, as we mark them as 1, should be equal to the total number of queens that we have. Then we define two variables, like you can see here, Xij and Xik. Xij, it means a queen is in the row I and column J. Xik, it means another queen in the same row but in different column, right? K is different. So these two variables can be in 4 conditions, like 0, 0, 0, 1, 1, 0, and 1 and 1. But the last one is not possible. 1 and 1 is not possible because they kill each other. In general, this constraint says that in each row there must be one queen only. We can do the same thing for the other column as well. As you can see here, this constraint 4 and 5, these are for diagonal, that there must be no 2 queens in each one, right? So this is constraint for taking care of diagonals. One for the diagonal that goes from down to up and from left to right, and the other one here, you can see this is for the diagonal that goes from up to down and right to left. We can formulate the n-queen problem in another way as well, formulation number 2. So here we define our variables as q1 to qn, the number of queens that we have. Then we show that queen is in the first cell. For example, if we put it in column number 1, right? Then each variable qi, like q1, q up to qn, can have a value. For example, 1, 2, 4 in this example that we have. So when we say q1 is equal to 2, it means the queen of the first row is located in column number 2, right? In this way, we can continue, right? So you can see here, queen number 1 is located in here, or this the second row is q2 is equal to 4, q3 is equal to 1, q4 is equal to 3, right? So here we have a domain, and this is the number of column, which is equal to the number of rows, right? So the number of column and the number of queen is also in the board with n to n, right? Number of rows, number of columns. Now we can define the constraints. We can go for implicit way or explicit way. In implicit way, for all I and j, there must be no queen like qi and qj where they can kill each other. And in case of explicit, when we say if q1 is equal to 1, then q2 cannot be equal to 1 or 2, right? So q1, q2, 1 or 3, 1 or 4. This second formulation that we defined here is better than the previous one because it has less number of variables. Let's go back to the Australian map coloring. Each constraint related to variables at most. If you want to plot the graph, nodes are variables and arcs are constraints, right? So here is a graph. So this is node, province, 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 province. As you can see here, this node has no arc. It means it has no constraint. It can get any value, right? It can get any color because it has no border, right? But this WA has a constraint with NT. WA has a constraint with SA. WA has no constraint with T, right? So in this way, we can try it. It means if two variables are in conflict, there will be a link between them. So general purpose CSP algorithm use the graph structure to speed up search. For example, as you can see here, Tasmania is an independent sub-problem. So we consider this as a one sub-problem, and this is a sub-problem. Another type of problem that we can solve using CSP algorithm is crypto-arithmetic. So in here, each letter is a representative of a number. You can see here, you have TWO is equal to FOUR, right? These letters, each one is representing a number, right? So we should find out the numbers that these letters represent to have this correct calculation. And also two letters cannot have the same value. So variables are the letters, and also we have some carry here, right? For example, O plus O, if for example O is equal to 6, then 2 will come to here and 1 is carry here. Our variables are these letters that we have, F, T, U, W, R, O, X1 and X2 as, you can say X3 as carries. And domain for each one is 0 to 9, right? So each letter can represent a number from 0. We have constraints, right? So these are the constraints. All diff, it means these letters cannot have the same value. They must be different. Then the sum rule should not be violated, right? So O plus O is equal to R, that you can see here, plus 10 multiply X1, right? So for example, 6 plus 6, 6 plus 6 is equal to 2 plus 10 multiply 1, right? And in the same case here, W plus W is U plus 10 multiply X2, and T plus T is equal to O plus 10 multiply X3, and finally F is equal to X3. These are the constraints. So we can show them like a graph. Using a graph, we can easily solve a problem. We can find a solution using graph according to the constraints, right? So for this example, O as 7 and R as 4, then we have W as 6, right? 13 and then 17, right? So you can see here, T is equal to 8, T is equal to 8, and W is equal to 6, and U is equal to 3, and F is equal to 1. So this is okay, right? CSP can help us how to solve these crypto-arithmetic problems. Sudoku is also a CSP. In Sudoku, initially, some cells have values, but some of them have no value. Our variables are those cells that has no value, and we want to find an appropriate value for each cell. Each cell can get a value from 1 to 9. So we have several constraints here. So each column in here, they should not have the same value. It means they should be all different, right? Rows also should have different values, and also regions, right? Each region, we should not have repeating numbers. So these are called as constraints for Sudoku. We can have different CSPs according to their variables types. Two possible types we can envision for such problems. One is discrete variables, and another one is continuous variables. In case of discrete variables, it means the domain of variable is discrete. For example, map coloring, right? So we can have finite domain as well as infinite domain. In finite domain, the big O is D in power of n. This is the different combination if D is value and n is a variable. For example, Boolean CSP, map coloring, n queens. And also we may have infinite domain like integer, strings, like scheduling problems. On the other side, we have continuous variables. So like time, okay, telescope start to observe the sky in a continuous time, for example. Also, we may have different type of constraints. For example, each constraint is applicable to one variable only or several variables. So we have unary constraints. Unary, it means one constraint is applicable only to one variable. Binary constraint, it means two variables are in conflict of each other. Also, we can go for higher order of constraint like Sudoku and crypto arithmetics. Some constraints are called as hard constraints and others are called as soft constraints. So hard constraints are mandatory and must be satisfied. However, soft constraint, it means it is recommended to do so, but it's not a must. There are many real-world CSP problems like assignment problem, timetabling problem, hardware configuration, transportation scheduling, factory scheduling, circuit layout, fault diagnosis, and many real-world problems involve real-valued variables. Now, we want to learn how to solve CSPs. First, we need to do standard search formulation for CSP. For formulation, we need to define states. For example, we have n variables. Some of them got some values. These are partial assignment. At the beginning, initially, we don't have any variable with an assigned value. For successor function, we select one of the values and assign it to one variable that has no value so far. Our goal test is to take care of hard constraints that do not be violated. Also, we need to take care that all the variables got a value. It means it is complete. To solve, we try to use traditional algorithms to solve CSP. If it doesn't work, then we will try to improve it. For example, we will start with the straightforward naive simple approach, then we try to improve that one. For example, we want to use BFS, breadth first search algorithm, to solve a CSP. Whereas the goal states are located at the last level for a solution, the whole tree needs to be explored. So we have like graphs here. We start from WA in this example. We assign one value, for example, red to this one. Then we go for the successors like NT and SA. Then by taking care of the constraint, it means no similar value like red can be assigned here. For example, we can go for blue in this one. Then we go in BFS mode to NT and we take care that two value already assigned to here. The remaining one is green here. In the case of BFS, we need to traverse all the graph to have a solution. However, the problem is here that maybe at the end, leaves, there are some nodes that cannot receive a value. Why? Because of the constraint that we have. In this case, the time and space complexity will be so high. For example, it can be like B of B in power of n. That is too high. So let's see how DFS works. We start from the root and we go to the depth instead of breadth. If we have n variables, then the depth is equal to n, right? In this case, the best solution may be found at the n depth. For example, we have x1, x2 up to xn, and if di is the value for each variable I, then the branching factor is the sum of the values that we have assigned. It means the remaining values that left free to be assigned to a variable. It seems that the branch factor is so large, and we see that DFS is a candidate solution, but it needs to be improved. For example, in the case of n queens, we start from the first line and we allocate one queen, then we go to the next line, right? So you can see here we assign n queen here, then we go to the next line. So this is an improvement to DFS, just we assign value to one variable at each time. But there is one problem. At each time we are assigning values to variables, but we have to take care of constraint as well. In this case, we need to go back and change some of the variables that already got a value. But still, maybe we are in a case that there is no solution. It means we come to some point that we cannot allocate queen to any point because the constraints have been violated by the previous variables. Why it happens? The reason is we did not care about the constraint. In this case, we need to study a new solution that is called as backtracking. In backtracking, if a constraint has been violated, we need to stop immediately. We go back and change the values and we try another route. What we are going to do is going to make two improvements to DFS. One, we take care of the assignment ordering, and the other one, we take care of the constraints. Here, we want to see one algorithm to solve CSP that is called as backtracking search. This is the basic uninformed algorithm for solving CSPs. We try to assign values to only one variable at each time in each level. So, for example, x1 is assigned by a value. Then we go for x2 and so on. If WA is red, for example here, then NT can be green. We consider a fixed combination for the assignment. This is like NT green, then WA red. And while we are going forward, we strictly take care of the constraints. We consider only values which do not conflict previous assignments. In this case, we might have to do some computation to check the constraints. DFS with these two improvements is called as backtracking search. Backtracking search is an improved DFS. So let's see Australian map coloring example. At the first, no value is assigned to any variable. In the next level, we assign a value to SA. So we have three successors: SA red, SA green, SA blue, right? This is the possible colors that we can give to this one. If it is red, then next time we have two children, right? This province can get green or blue. In the next round, if we assign red and green, then for this province, we have only two values, red or blue. So in this way, we can create our search tree. Here is the backtracking algorithm. In backtracking algorithm, we consider searching every possible combination in order to solve the computational problem. It's a kind of recursive algorithm, and this is based on depth-first search. Backtracking chooses values from one variable at a time and backtracks when a variable has no legal value left to assign. This algorithm extends the current assignment to generate successors rather than copying them. Because the representation of CSP is standardized, there is no need to supply backtracking search with a domain-specific initial state, successor function, or even goal state. The functions select unassigned variables and order domain values, and order domain values can be used to implement the general purpose heuristic as well. So we can say that backtracking is DFS plus variable ordering and fail on violation. We learned that if any constraint is violated, we need to go back and change our assignment. Let's see how we can improve backtracking algorithm. There are several ways, including filtering, ordering, and structure. It means how we can utilize the structure of constraint to find out the solution easily. In ordering, which variable needs to be selected is important. And also the order that we should pick up the values and assign them to the variable is important. In the case of filtering, we want to predict the future failures and prevent them. How? In the case of n queens, when we assign one queen to one cell, for example here, then we remove this line, we remove that column, and also we remove the diagonals related to this cell. Let's see how filtering can help us. We try to remove useless values from the domain of the unassigned variables. So we have forward checking. This forward checking removes the values that if assigned to the current variable, this will violate a constraint. We consider only the allowed value that can be assigned, and we terminated if there is no allowed value to be assigned. So you can see here in this figure, first we can see that the domain is all, right? So it means we can assign all three to WA, all three to NT, all three to Q, and the rest. So you can see everyone has a value. Then when we assign red to WA, right, red is assigned to WA, then from the domain of NT and SA, red is removed, right? So we cannot assign red to these two provinces anymore. Then when we assign this green to this one, then green is removed from NT, this one, and SA because it's a neighbor, right? So SA is removed, and also from NSW, from this one also we have removed it, right? In the next state, when we assign blue to V, so then from this province, NSW, blue is removed, right? And also from this province, SA, blue is removed, right? But you can see here, there is one problem, right? It means there is no remaining value for SA, and we cannot assign any value to SA. This is the problem. We should take care of this problem. So the problem here is this way cannot detect all the future failures. Although the forward checking propagates information from assigned variables to unassigned variables, it cannot provide early detection of all failures. So for example here, if we start by WA as red in here, and then we remove red from NT and SW, so in here we remove these two, then we assign Q as green, and then we remove green from NT and also NSW and SA, then you can see these two have only one value left, blue. But NT and SW, they are neighbors, and they cannot get the same value. So this is another problem. So in this case, we have to stop. The solution is constraint propagation as another type of filtering. To understand the constraint propagation, we need to learn consistency of a single arc. In our graph, the nodes are the variables, as I explained, and arcs are the constraints. We define consistency of a single arc as if there is a direct link from X to Y for each value in X, there must be at least one value for this one in Y that does not violate the constraints. So you can see here, once we do forward checking, then we go for backward checking, right? So in here, we have, see the constraint, right? This is the constraint from NT to WA and also from Q to here, right? Because whatever we decide here, it has an impact on the value that we can go for Q. So this is the problem that we studied in the previous slide here that cannot be detected using forward checking. So in here, first we assign red to WA and we remove red from NT and SA. And we do like what we did in the previous slides. So consider the case of SA and NSW, right? So NSA and NSW here. There is a link between SA and NSW. It means they have a constraint, right? They are in neighbor. We want to check whether these links is consistent or not. If not, we try to do consistency. Consistency means for each value in SA, there should be at least one consistent value in NSW as well. Consistent, it means can be assigned. If SA is blue, in NSW, we have blue and red. Red is consistent because we can assign it, but blue is not consistent. Let's consider the opposite direction from NSW to SA. From NSW to SA. If NSW is red, then it's okay because SA can get the blue value. But if NSW get blue, then there is no consistency and we should remove the blue from SA. NSW has our consistency with Q and V. Why? Because green can be assigned to here, it's okay. And in this case, if we assign V to Q, there is no problem here. So still, we can have two colors, right? So and one can be go for NSW and these three can go to V, right? Because maybe a consistency has been broken due to deletion of blue from NSW and then they can get any value. This is the arc consistency algorithm for CSP. This is a simple loop. We have input. Input is CSP, including the variables and constraint that we have. This is a kind of binary CSP. It means each constraint is applicable to two variables only. It means the graph is binary. In crypto arithmetic, we had some non-binary graphs where one node has more than two links to others. Then we have some local variables. It's a queue of arcs in our CSP. And then here we have a while loop. We select the first arc in our queue. Then we check whether it is consistent or not. If there is direct link from x to y, for each value in x, there must be at least one in y that does not violate the constraints. Then we define a function to check the consistency here. The function that you can see, we name it as remove inconsistent values. This function checks whether an arc is consistent or not. If we need to do consistency, like remove something from the domain, it will return true. If it is consistent and we don't need to do anything, it will return false. The runtime of this algorithm, big O n squared t3, this can be reduced to n squared d squared. But detecting all possible future problem is an NP-hard problem. Now, let's discuss the limitation of arc consistency algorithm. Using this algorithm, we try to make a consistency for all the arcs. However, there are some side effects for this procedure. It is possible that there will be only one solution remain. It is possible to have more than one solution, or even it is possible that no solution remain there. So in this figure that you can see here, if we select red for this one, then there will be two solutions remain, right? For example, this one can get green or blue. It's okay, right? If we assign blue to this one can be green. If we assign green to here, this can be blue. It's okay, right? All the arcs are consistent in this graph. Still, there are some problems that arc consistency cannot detect all failures that may happen in future. In this figure here, if we consider the arc one by one, all are consistent. However, the problem, it has no solution, because if we assign red to here, right, we need to assign blue to these two. No solution, right? If we assign blue to here, we need to go for red to these two, and there's no solution here. To solve this problem, we need to run arc consistency inside a backtracking search. And also, we need to run it after each assignment, as well as we can somehow improve the arc consistency. We are learning how to improve the arc consistency by increasing degree of consistency. We can discuss the arc consistency in terms of the degree of consistency. For example, 1 consistency, 2 consistency, k consistency. In the case of 1 consistency, we take care of only one node. In here, the domain of each node has a value that satisfies all unary, or you can say single constraints. Unary, it means one constraint is applicable only to one variable. 1 consistency is called as node consistency. 2 consistency is called as arc consistency. So in the case of arc consistency, for each pair of nodes, each constraint assignment can be applied to the other nodes as well. For 2 nodes, if we can have a constraint assignment, then we can extend it to the next node in such a way that no constraint will be violated. So you can see here in this figure, we saw that this was not possible to predict the future value. But if we apply 3 consistency, we can predict the failure. It means we consider 3 nodes together and we check the consistency, not only 2 of them. A higher k is more expensive to compute. It means computational complexity will be very high. A strong consistency means a case that satisfies all degree of consistency, like 1, 2, 3, up to n. So a consistency is called as strong if k consistency is confirmed. The lower level of consistency also confirmed. If we have strong consistency, it means we can solve without backtracking. This is an analytic proof here. You can follow it. We select any assignment to any variable freely at the beginning. Then we consider the next variable. First, we apply 2 consistency that give the choice consistent with the first. Then we select the next variable and we apply 3 consistency where there is an option consistent with the first 2. Remember that we are trying to improve the backtracking algorithm using filtering, ordering, and graph structure. Ordering is the second try. It means what order we follow for the assigning the values to the variables. Everyone in this world lives based on his/her choices. Everyone in this world makes some mistakes. It's very common, but the successful people try to detect their failures early and go back and correct it. So here we have minimum remaining values, MRV. This algorithm says that select a variable that has the minimum values in its domain. At first, all variable has the same number of values in their domain. We randomly select one and give red color to it. Next, we have 6 unassigned variables. We select one with the minimum number of values in each domain. Then we selected green, and so on. We can continue. Least constraint values. After selecting a variable, we assign a value that calls least constraints. It means the value that removes less number of values from the domain. Such kind of selection needs to do refiltering and hence needs more computations. So in this figure, we can select either red or blue. You can see here, red or blue. We select one of them that calls less constraints. We select red because it removes less number of values from the domain of other nodes. Okay, let's check our backtracking search algorithm again. Basic backtracking search is based on DFS. We select a value for each variable every time. If there is no valid value to assign to a variable, we return to a step back. So we have a function here, recursive backtracking, and if assignment is complete, then return assignment. If the assignment is completed already, then we will have the assignment policy that we have learned. Then we have order domain values. This is to know which value should be selected first. So in the if condition, if the value is consistent with the assignment according to each constraint, then it will add the variable value pair to our plan. Otherwise, if fails, it goes back and select another variable. Once again, we are trying to improve our backtracking algorithm using filtering, ordering, and structure. So now we want to learn graph structure, and we want to see how the graph structure helps us to improve backtracking in order to find a solution soon. So you can see here, Tasmania has no border with the other 6 provinces. It means there's no arc. This graph has 2 parts. We have 6 nodes here and 1 node in here. If n is the number of variables, and we can separate them into some subgraph with like C variables, then the number of independent subgraph will be n divided by C. And if D is the number of values in the domain, so the state space of subgraph is D in power of C. And if we separate it, then the number of computational will be 2 less. For example, we have a graph of 80 nodes, and they are binary, and we consider C as a subproblem of variable like 20. So if it is a connected graph, like single graph, D in power of n to power of 80, it takes 4 billion years at 10 millisecond node if you want to try this one. So it means if we have 10 million nodes per second processing, then it takes 4 billion years to compute. But if we divide it into 4 subgraphs and each one with 20, right? So then 8 divided by 20 is multiplied 2 in power of 20 takes only 0.4 seconds if we are processing 10 million nodes per second. So it will be too fast. So you can see here, this figure is another example, and this is our constraint graph. Each arc, it means there is a constraint between the nodes, between C and B, between A and B, but there is no constraint between B and E and B and F. Trees are good cases for CSPs because it is linear. So we have a theorem here. If there is no loop in our constraint graph, then the complexity of the algorithm will be equal to n multiplied d squared. This is much better than the general case of CSP when we have big O of d in power of n. So for tree structure CSPs, let's see an algorithm called topological ordering. We saw that a linear structure has a better complexity in the previous slide. So it's a good option to convert the graph into a linear structure. We need to follow some properties. So in this figure, you can see here, we select one of the node as root, like A as the root. Then we convert the arcs to directional arcs, right? So these are unidirectional arcs, but you can see here directional based on the constraint. So it means from A to B, we have a constraint. From B to C and B to D, you can see B to C, B to D here. Then from C, we don't have any constraint. From D to E and F, we have constraints, right? Now we want to apply the topological ordering. Each parent should be before his children. So in figure, each parent is before each children that you can see here. Once we have made this tree, then we start from right to left and remove the constraints. We can see the domain for each variable under the nodes that you can see here from right to left, not from left to right, right? From here to here. So there are 2 steps, backward removal and forward value assigning. In the first step, we will try to remove the same values, right? So blue is here in F. So blue is in here, F. Then we go back and we remove blue from D, right? Then in here, if we have blue and green for E, right? And we should remove green from D, right? Because children. Then we have only red in D. So red should be removed. Then when we come to C, we can have green, and green is removed from B, right? And then in here is here, and blue is in B, and blue is removed from A. So we do our consistency from right to left between each parent and its children. Then we apply forward value assigning, right? So this one, red for A, blue for B, green for C, red for D, blue for E, and blue for F. In this case, the runtime is big O of n d squared. In this Australia map coloring, if we remove SA, then we have a tree like this, WA, NTQ, NSW, and this one is separated. So we consider SA as a separate node, then we can have a tree. First, we initiate a variable and remove its neighboring domain. Then we apply Cutset conditioning. Cutset conditioning, it means we select a node by removing which the remaining graph will be a tree, right? Like SA we remove, and we have a tree. This is a graph. This is a tree. There's no cycle. In this way, we can improve the complexity. Let's see how Cutset works. This example, we have a wheel-shaped graph. As you can see, if you remove SA, it's easy to make a linear tree. First, we select the Cutset of SA and we remove SA. Then we select the domain of SA, red, green, and blue, right? So this is our tree in the first step. We remove this one, and we consider that this SA can get red, green, or blue. Then, according to our selection, we can continue the graph as a separate tree structure graph, and simply we can solve this one. So in here, if this is red, then we can start this one as blue, green, then we can continue the rest of our tree. So let's see the tree decomposition. We want to have a graph of mega variables in a tree structure fashion. What is the meaning of mega variable? Mega variable, it means multiple nodes that are considered as one node. So for example, we have M1 here, and M1 is considered of three nodes, WA, NT, and SA. Each mega variable encodes a part of original CSP. In order to ensure consistent solution, we allow overlap between our problem. This is a tree structure, and we simply can solve this one, right? We take care of constraint in each mega node, then also between them, we also take care, right? So we made sub problems. So local search methods typically work with complete states. Complete state, it means all variables are assigned. To apply a local search methods to CSP, we take an assignment with unsatisfied constraint, then we operate reassign variable values, and if there is no fringe, we leave on the edge. So then we have mean conflict algorithm. While not solved, then we go for variable selection and value selection. In case of variable selection, we randomly select any conflicted variable, and then in the case of value selection, we go for mean conflict heuristic. In this case, we choose a value that violates the fewest constraint. For example, hill climbing with heuristic of n as total number of violated constraints. Okay, that's all for this lecture. CSP, constraint satisfaction problems, are special kind of search problems. In here we have states are partial assignments, and the goal test is defined by a constraint. We have like basic solution of backtracking search. Then we studied filtering, ordering, and structure to improve this backtracking search. Thank you very much for your attention, and please feel free to ask me if you have any questions. Thank you, and see you in the next lecture.